When you glance at your phone for the time, have you ever really stopped to think about it? I mean, where does that number actually come from? How does anyone know for sure what 1 second is? Well, we're going to dive into that because the answer isn't in some gear or a crystal, it's deep inside the quantum world.
Right. This is the big question. It sounds so simple, but honestly, humanity has been chasing a perfect definition for centuries. We tried tying it to the Earth's spin or the swing of a pendulum, but none of those are truly constant. We needed a better, more perfect ruler for time itself.
And this just shows you the journey we've been on, from looking at the sky to building complex machines, and now to the quantum realm. I mean, think about it. Every step before this had a flaw. Sundials don't work in the dark. Pendulums get fussy with temperature and friction, and even those quartz crystals in your watch, they age, they drift. All those tiny errors just keep adding up. So to fix this, physicists realized they needed something that wasn't man-made, something way more stable. They needed a constant that was baked into the very fabric of nature, a rhythm that's the same here, on Mars, or in a galaxy billions of light years away, a rhythm that will never, ever change. And this is the brilliant leap. The key to perfect time wasn't about building a better machine. It was about finding a fundamental property of matter itself. The solution was right there all along, hiding inside every atom, in the super predictable, incredibly reliable jump of an electron. So, which atom is it? Well, the star of our show is one specific element, cesium-133. This atom has a kind of quantum tick-tock, a ridiculously stable transition between two of its energy levels. And that little tick provides the ultimate, unwavering reference for all of time. Okay, wow, that is the official definition. I know, it's a total mouthful. But here's the part that matters. A second is no longer just a fraction of a day. It's a specific, concrete number, over 9 billion of a single atomic event. We've defined our time based on a number that simply does not change. Period. This is the perfect way to picture it. Just imagine that every single cesium-133 atom in the entire universe is a perfect little tuning fork, and they all ring at the exact same frequency, forever. The whole job of an atomic clock is just to listen to that one perfect note. But there is a catch. And that catch is motion. You see, hot atoms are zipping around like crazy. Trying to hear their frequency is like listening to 100 little bells all flying past you at high speed. It's just a noisy, smeared-out mess. That's the Doppler effect. So to hear that pure, crystal clear note from our atomic tuning fork, we have to get the atoms to hold almost perfectly still. And that's where laser cooling becomes absolutely essential. So, how in the world does a machine actually listen to this perfect atomic rhythm? It's not about gears and springs, that's for sure. It's this really beautiful, elegant process where physics and electronics work together in perfect harmony. It really just boils down to these 3 steps. First, you prepare the atoms, get them super cold and hold them in place. Second, you let them interact with a microwave field. You're basically asking them, hey, is this the right frequency? Does this frequency make you tick? And finally, the electronics lock on to the frequency that gets the biggest response, making that perfect pitch the official heartbeat of the clock. Oh, this is my favorite part. The whole system is self-correcting. If the clock's own frequency starts to drift, even by a tiny, tiny amount, the atoms basically complain. Their response gets weaker, the electronics notice this dip immediately and nudge the frequency right back into that sweet spot. The atoms themselves are the referees that keep the clock honest. Now, I know this all might sound like really abstract physics, but the crazy precision we've been talking about, it's not just for science labs. It is quietly running our entire modern world. It's in your car, it's in your pocket, it's everywhere. Seriously, think about it. Your GPS, the stock market, where trades happen in microseconds, the internet itself, even the power grid that keeps the lights on. All of these things rely on thousands of different devices all agreeing on the exact same time, down to the billionth of a second. And where does that agreement come from? Atomic clocks. And GPS is just the perfect example. Your phone figures out where you are by measuring the tiny, tiny difference in the time it takes to get signals from different satellites. A nanosecond is a billionth of a second. If a satellite's clock is off by just a handful of those, your GPS would be off by several meters. It would put you in the middle of the road instead of on the sidewalk. That's how much this precision matters. So we found this incredible standard with cesium. It's amazing. But you know how science works. Good enough is never really good enough. The question is always, can we do even better? And the answer is yes. The quest for even crazier precision is pushing us beyond cesium. So, say hello to the next generation, optical clocks. These use atoms that tick way, way faster, at frequencies in the optical range, like visible light. A faster tick means you can slice time into much finer pieces. It's like switching from a ruler that has millimeter marks to one that has nanometer marks. You can just measure things with so much more detail. And the level of precision we're talking about here is, well, it's kind of hard to wrap your head around. Some of these new experimental clocks are so stable that if you could have started one at the Big Bang and let it run until today, that's almost 14 billion years, it would be off by less than a single second. It's just staggering. And that really brings us to the core takeaway. This whole adventure isn't just about building a better clock. It's about taking our human idea of a second and anchoring it to a fundamental, unchangeable law of the cosmos. We have literally tied our daily schedules to the quantum pulse of reality itself. So I'll just leave you with this final thought. By understanding the atom this deeply, we've completely redefined the very foundation of how we measure our own existence. And it just makes you wonder, if we can do that for something as fundamental as time, what other basic concepts are we on the verge of redefining next?